students. So the next speaker is Raaghav from UC Santa Barbara, who will talk about the influence of cohesion and particle size on yield stress of granular materials. Thank you.
Okay, so I'm a third year undergraduate student in All Arts lab at UCSB. And let's see. So let's imagine that you're like walking on the beach, right? And as you're walking, you have your shoes on, and you don't really want to walk in the dry sand because then it's gonna get everywhere, right? So you walk a little bit closer to the ocean, but you can't get too close because obviously the water's there. And so you try to find that nice sweet spot where you're not sinking into the sand and there's some resistance in that material. It's still the same dry material, except that now you have a little bit of water in between the particles of sand, and so that's adding some strength to the material. So this is some sand pretty close to the water, and this is some just like a little ways away. Both of them are relatively damp, and I've removed my foot for scale that's like maybe 250 newtons of load on the sand, and as you can see, there's like barely any deformation. So why has this changed so much since we just added a little bit of water, right? So we think that this is because of cohesion. So in a fluid, you think of this as like, I don't know, the tiny forces between the molecules holding each other together, but at a larger scale, it's the same idea, except you have fluid interacting with larger particles. So with our sand, we have a lot of different things here, but we try to simplify it a little bit, and we see that there's some strength that develops when you add some source of cohesion. So we don't really think that it has to be like just water. It could really be from a number of sources. So some things that we've tested are with like polymer coatings on grains. And so obviously sand is not perfect spheres like this, but for the sake of our tests, we have to start somewhere, right? So we simplify it. We have these, we add a little bit of water to our system, and they form these bridges between particles. And for the polymer coatings, you coat the sand, and there's some cross-linking in the polymers that adds cohesion to your system. So we use this bond number to characterize the connection between just two particles, but we're more interested in like a larger scale. So we want to like not worry too much about the exact source of cohesion, but rather that the material is developing some strength due to some source. So if you have just one particle and it's dry, there's no cohesion, when it slips, it's going to slip like it's just friction, right? So something interesting happens at the bulk scale. You develop this strength. So as you see here on this side, the cliff is like, it's got an angle of repose that's like greater than 90 actually, which is really weird. And down here, it's holding a lot more shape than the dry sand before. And so some data that we have show that when you apply some load to your bulk material and look at where it fails, as you approach the limit, there's no load applied, your cohesion-less system has an intercept of 0, but this intercept increases when you add cohesion to your system. And so these are two different sources of cohesion, but they act in the same way. And so this is how we've tested this. So we have a bulk of material on top of inclined plane, and as we increase the setup, or the angle here, it starts to fail. And so the limiting thing here is that we can only really apply the same load as the weight of the grains here, because we're looking at when it fails against that 2D plane on the bottom surface. And so we can't really figure out what happens at higher loads, and we also can't see what happens when you're at a very low cohesion level, because the material will fail due to very small instabilities. So this makes it a little bit difficult, and so we want to move to a new system. But before that, let's talk about the cohesion number. So this is similar to the bond number. It's actually the inverse, or it's proportionally inverse to the bond number. So you see that we're relating the cohesion force in the system to the weight of the system. And so we can use this to characterize the yield strength of the material, or the yield stress of the material. And so to get over those drawbacks from the inclined plane, we have a new setup now, which is a shear saw. So why not just a cylinder? Well, as you get to the very center of the system, you have some irregularities, so we go with an annulus. And this allows us to measure much larger loads, and so this is our system. We hold the bottom of the cylinder and rotate it, and then to the top we apply some known force, and so that's our compression, compressive force in the material. And so we induce some stress, and we measure the torque that builds up in the system, and we'll notice that it's it starts to rise up there a little bit, and then at some point the material yields, and so the stress drops again. And so this is a way that we can gather a lot of data, because we don't have to reset our entire system. We can just run it again. There's another, just keep going for more cycles, and we can test a much wider parameter space. And so some preliminary data that we've gotten shows that it kind of aligns with our inclined plane, and we haven't exactly gotten down to the same scale, because the system itself has some weight, but we have some ideas on how to decrease the load. So some future work, we'd like to see what happens when you vary the grain sizes. So all of our tests so far have been done with one size particle, and in real life that's definitely not the case. Sand has a wide particle distribution. Most systems you can think of in nature are not going to be identically sized particles. So we'd like to see if changing the average size of the grains leads to something different in the material's yield strength. And we have density in our cohesion number. We'd like to see if that changes much, but that's not as interesting of a question yet. And yeah, that's it. And this is Ram, and I'll run the work.
Okay, thank you. Questions for Raaghav?
How do you think the yield stress might be affected by having a polydisperse set of sizes?
So as you have, well, okay, there's a paper that was published very recently using numerical analysis. I haven't had the time to read this. I think it was a week ago, but it seems like it increases non-linearly, not in the same way that we see changing the diameter would change the yield stress. So when you have multiple sized grains, they're gonna arrange themselves in a very weird pattern. It's not as easy to characterize, because the number of contacts between the grains changes, and something also important is like how much liquid you have in the system, because our model here, we only add a tiny bit so that they stay in those nice bridges between two particles. But obviously, if you have a large range, adding a little bit of fluid might completely engulf one particle, whereas it's still forming a small bridge with the others.
Questions? I have one. You're adding polymers to these particles. As you do more experiments, do you see any change in the yield stress behavior? I can imagine that the polymers might get worn off the particles because of friction or other things.
So we haven't tested polymers in the shear cell yet, but in over time you do have to reset polymers anyways because they start to degrade. So I would expect that for the polymer scenario, we would want to keep it keep a fresh coating on the grains. So that might be resetting our system more frequently.
I have a follow-up. Can you describe again the motivations for using the shear cell over the inclined plane? When you show your data, the inclined plane data looks much cleaner than the shear cell data. So what is the motivation for switching?
So here with the inclined plane, this is like maybe, I don't know, weeks of work just to get those few data points, whereas this is like one day. So
that's strong motivation.
we get a lot more data really quickly. So
Okay.
the error bars are probably due to vibrations in our system. So I think we can try narrowing it down and also being more careful with how we add water to the system. Yeah.
I had a question about the data on the slide before this. I was wondering if you have any ideas about what the second peak might be.
Okay. So first, looking at the time scale on the bottom, this is 300 seconds. We rotate our cell really slowly, so this is like half of a cycle. And so the second peak could be from some irregularity in the shape of our cylinder, where it kind of oscillates and we have like some periodic motion introduced due to that. But another thing that we've seen in literature is this is like our point of yield, and this is, I think, a point of incipient yield. And so the material fails and then is still in some organization of grains where it has a little bit of strength, and so the stress builds again a little bit and then fails back to like the base state.